Hello and welcome to the third part of this introduction into reinforced concrete design. Today we are going to speak about the design philosophy adopted by the Eurocodes. There are several Eurocodes that are related to the design of reinforced concrete structures. They include Eurocodes 0, 1 and 2. Eurocode 0 establishes principles of design, Eurocode 1 defines loads on structures, and Eurocode 2 defines the principles of design of concrete structures, including buildings, bridges, reservoirs and dams, as well as design for fire resistance. When there is a need for guidance on a subject that is not covered by the Eurocodes, a country can choose to publish documents that contain non-contradictory, complementary information that supports the Eurocodes. In the UK, Eurocode 2 is supported by several documents that are non-contradictory and complementary. For example, PD 6687 provides additional information on the design of buildings and bridges, and BSEN 206-1 contains information on concrete, and BSEN 10080 on the reinforcing steel. The design procedures and parameters adopted by the Eurocodes can be amended in each country by national annexes. These are based on reasons of safety, economy and durability. In the UK, the national annexes are published by the British Standard Institution. Before we proceed further, we should consider the Eurocodes terminology. According to the code, action means a load or imposed deformation. Examples of actions include weight of structural and non-structural elements, snow and wind, as well as temperature effects and settlement. The effects of actions represent the response of a structure to the applied actions. This includes internal moments and forces, bending moments, shear forces, and deformations caused by actions. Strength is a mechanical property of a material, in units of stress. Resistance is a mechanical property of a cross-section or a structural element or an entire structure. It should be noted that strength is quite often used in the meaning of resistance, but these two terms should be distinguished. Let's now look at the design philosophy adopted by the Eurocodes. Eurocode 0 is the first Eurocode. It introduces principles of design and variables involved. The design is based on limit states, while design safety is assured using the partial factor method. In this method, partial safety factors are applied separately to actions and resistance. This allows the design to achieve an overall level of reliability for a given return period, that is, the design life of the structure. In this series of lectures, we will consider two limit states: the ultimate limit state, or ULS, and the serviceability limit state, or SLS. The ultimate limit state deals with strength and safety of a structure and aims to prevent its failure or collapse. The serviceability limit state is concerned with the condition and appearance of a structure and governs its stiffness. It aims to prevent excessive deformation, cracking and vibration. If we consider the schematic load deformation curve in the diagram shown on this slide, the SLS governs the first two stages of loading with low and middle levels of loading, while the ULS governs the last stage of loading, i.e. the load causing structural failure. The design for the ultimate limit state requires us to satisfy the following condition: that the design effects of applied action, that is, internal forces, moments and so on, are smaller than the design resistance. The ULS considers several situations, including conditions of normal use, transient temporary or transient conditions, for example, conditions occurring during construction, accidental situations and seismic situations. The effect of actions is considered for several actions occurring simultaneously. These actions include permanent and variable actions. In this formula, you can see the partial safety factors, the Greek letter gamma, apply to all actions that take account of uncertainties in the values and modelling of these actions. An additional partial factor for combination, given according to the Greek letter psi, is applied on accompanying variable actions to account for the lower level of these actions occurring together with the leading variable actions. The design for the serviceability limit state requires us to satisfy the following condition: that the design effects of applied action, that is, internal forces, moments and so on, are smaller than the limiting design value of the relevant criterion, such as the onset of permanent deformation, crack width, etc. The serviceability limit state considers several situations, including characteristic loading combinations, frequent loading combination, and quasi-permanent loading combinations. The characteristic loading combination is used for checking that no inelastic response occurs. The frequent loading combination is used if deflection needs to be checked, and the quasi-permanent loading combination is used for checking long-term effects such as degradation of structural stiffness due to creep. As you can see in the formulas describing these loading combinations, the partial factors are not applied to actions. This table is taken from the UK National Annex to Eurocode 0. It introduces corrections to the values of combination factors for buildings given by Eurocode 0. This table gives typical values for the partial factors for actions at the ultimate and serviceability limit states. As you can see, the partial factor for the permanent actions at ULS is 1.35, while the partial factor for the variable actions is 1.5. The larger safety factor reflects the larger uncertainty in the values of the variable actions. Since the partial factors at ULS are larger than 1, they increase the effects of actions. All partial factors equal 1 at SLS and therefore do not change the effects of actions. The design resistance is generally defined by Eurocode 0 using the following formula. The design resistance is divided by the partial factor for material, gamma mi. Since this partial factor is larger than 1, resistance is reduced. This table gives the values of partial factors for different materials. As you can see, the partial factor for material equals 1.15 for reinforcing steel and 1.5 for concrete. The larger value of this factor means that there is much larger uncertainty in the strength of concrete. Therefore, a substantially lower strength is used in the design. Let's now look at some different actions as defined by Eurocode 1. These actions are divided into permanent actions, also used to be called dead loads, and variable actions, which we used to call live loads in the British standards. The permanent or dead loads include the weight of structural elements and non-structural components. The structural elements are those that carry loads. They include beams, slabs, columns, walls, etc. The non-structural components are being carried by the structural elements. They can include things like partitions, screed, false ceilings, service facilities, etc. Eurocode 1 divides the live loads into uniformly distributed loads, or UDLs, and concentrated loads, or CLs. The values of these loads are defined in accordance with the intent of use of the corresponding area. For example, residential, social, commercial, and administration areas are differentiated from areas for storage and industrial activities. Let's consider the example of residential, social, commercial, and administration areas. The live loads that are assumed to act on the floors depend on the categories of their specific uses. For example, a classroom will be classified as category C2. Eurocode 1 defines a range of values for the live loads in different categories. In the case of a classroom, which we said is category C2, the uniformly distributed load can be in the range of between 3 to 4 kN per square meters, while the concentrated load will be in the range of between 2.5 to 7 kilonewtons. The recommended values are underlined in the table. Let's move on now to look at the material properties of concrete and reinforcing steel. As mentioned in the first part of this introduction, there are two types of standardized tests used for establishing the compression strength of concrete, cube and cylinder. Each test gives a different value of strength. As a result, the concrete strength can be defined either as cube strength or cylinder strength. The concrete strength defines its class. The values of both types of strength are given in Eurocode 2 for each class of concrete. For example, the concrete class C25/30 means that it has the cylinder strength of 25 megapascal and cube strength of 30 megapascal, all at 28 days. Eurocode 2 also defines the tension strength of concrete and the modulus of elasticity for each concrete class. The values of strength shown here are the characteristic values. The design compressive strength, FCD, is obtained by dividing the characteristic strength, FCK, by a safety factor for material and by multiplying it by a parameter alpha cc. Here, alpha cc is required to account for differences in the stress rates of concrete during bending in a structure and during testing in a cylindric specimen. The stress strain curve shown in the top diagram is typical for a compression test. As you can see, the curve is nonlinear and difficult to describe using an analytical expression. Such complex curves are used in numerical and finite element analysis of concrete structures. Since the real stress-strain curve is highly nonlinear, concrete behaviour and design can be described using different, simple stress-strain curves. Here you can see two such examples. The diagram on the left shows the parabolic rectangular curve, and on the right we can see the bilinear curve. Higher strength concretes are more brittle. This behaviour of high strength concrete is accounted for in the design by shorter horizontal branches in both diagrams. The characteristic yield strength of reinforcing steel is defined as 0.2% proof stress. In the UK, the value of characteristic yield strength of reinforcing steel is taken as equal to 500 megapascals and the elastic modulus as 200 gigapascals. Reinforcing bars are manufactured with ribs to create mechanical interlocking between bars and surrounding concrete. Different forms of deformed bars were used in the past, and here you can see a few historical examples of deformed reinforcing bars. Reinforcing bars can be manufactured using two different processes, hot rolling or cold forming. Hot rolled bars are more ductile, while cold formed bars are less ductile. The stress-strain curves describing tension behaviour of these two types of bars are shown on the right. The ductility of reinforcing bars is very important in the design of concrete structures. Therefore, the bars of three ductility classes, A, B and C, are used for different design purposes. The ductility class A is the cold formed bar. Ductility class B is hot rolled bars, and ductility class C is seismic reinforcement. From class A to C, the ductility of bars increases. This can be seen in the table in the increase of the characteristic strain at maximum force, epsilon UK. And to end this lecture, we'll speak about the methods of structural analysis adopted by the Eurocodes at the ultimate and serviceability limit states. There are three types of structural analysis considered in the design to the ultimate limit state, and they include linear elastic analysis with limited redistribution, and plastic analysis. Each analysis type should be appropriate to the problem considered. Only linear elastic analysis can be applied at the serviceability limit state. Linear elastic analysis is carried out based on several simplifying assumptions, and they include the following. Structural elements remain uncracked and their cross-sections remain plane at all loading stages. As a result, the analysis is based on concrete cross-sections. Structural materials are linear elastic, that is, they have linear stress-strain relationships. And the effect of imposed deformations is to be calculated with reduced stiffness and creep. This means that the value of the elastic modulus can be calculated as a mean between the values of the short-term and long-term elastic moduli. In the case of linear elastic analysis with limited redistribution, the inelastic nature of a concrete structure introduced by concrete cracking is partially accounted for by reducing and redistributing maximum moments to other parts of the structure. The redistribution is done by assuring that the moments and forces stay in equilibrium with the applied actions. The amount of redistribution moment depends on the ductility of a structure, which is defined by the class of concrete and reinforcement. Redistribution can reach 20% for continuous beams and slabs made of concrete classes, which are up to C50/60, and a reinforcement class A, and it can reach 30% for reinforcement classes B and C. While continuous beams and slabs are made of high-stress concrete, the redistribution limits the amount of concrete that can be used in calculations of flexural capacity of a reinforced concrete cross-section. This capacity of the reinforced concrete cross-section is defined by the X to D ratio, where X is the depth of concrete in compression, or the depth of the neutral axis, and D is the effective depth of the section. Both X and D can be seen in the schematic reinforced concrete cross-section shown in this picture, and will be discussed in much further detail in future lectures. Redistribution is not allowed for calculation of moments during the design of columns. Plastic analysis may be used for the design at the ultimate limit state only when the required ductility of the reinforced concrete cross-section can be assured. This is done by limiting the X to D ratio to X to D has to be equal or lower than 0.25 for concrete strength classes that are C50/60 and under, and to X over D of equal or under 0.15 for concrete strength classes that are over C50/60. Only Class B or C reinforcement can be used in structures designed using plastic analysis. Additionally, the ratio of bending moments at intermediate supports to moments in spans has to be in between 0.5 and 2. Join me next time to discuss fire resistance and durability of reinforced concrete, before we move on to tackle the design of structural elements.